So here is a video where I'm going to do a heuristic argument to derive the formula for the sum of the first n squares by using calculus. So we'll use this as a way to motivate the formula, and then at the end the verification will be a very simple induction. I like this method. I think it's very simple and clean. I think it would actually work for the sum of various powers like 0 cubed plus 1 cubed plus 2 cubed and so on. If you want to do integer powers all the way, it could work even for other recurrence relations. I haven't looked into that yet, but to me I like this approach. It avoids having to deal with a lot of summation symbols and having to move things around. So Desmos.com, that marvelous, magnificent website, has a new feature called Notebook, and I decided to go ahead and write this up there for clarity and speed, just to try to keep this short. So I'll talk us through it as we scroll down. So the sum of the first n squares is going to be 0 squared plus 1 squared dot 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 plus n squared. We're going to throw 0 squared in there for convenience. Just makes the subsequent work a little bit easier. So then the defining relation is that next relation. The sum of the first n plus 1 squared is the sum of the first n squares plus the square of the next number. So that defining relation is a recursion relation, a rather simple one. Now, let's just suppose, just trying our luck as a working hypothesis, since these points are all isolated anyway, that there are many smooth functions that hit these points, but let's extend S to a differentiable function and see what happens. So we have again this defining relationship here. I'm going to say S of x is now S of x minus 1 plus x squared. So we're just upgrading the recurrence to apply to x for x, in this case starting at 1. Again, we don't have to worry too much about domain issues at this point. Alright, so then I take the derivative, and notice that when I take the derivative here, I take the s prime, and then I take the derivative of the inside, but that's still 1 by the chain rule. So that gives me that, and then I take the derivative of x squared, I get 2x. So I take the derivative again, that gives me a second derivative here, same thing, second derivative here, chain rule leaves that alone, and then the 2x gets differentiated down to 2, and then take a third derivative, and voila, look at this, they're equal. So now what we're going to do is, just as a working hypothesis to see if it pans out, is to assume that's a constant. So if I have the third derivative as being a constant a, now instead of differentiating, I'm going to integrate. So we know that the general form for that is to have a constant. The second derivative now will be ax plus b, but we know from our relation up here, back when we were taking derivatives, that that's going to be the second derivative evaluated at x minus 1 plus 2. That's this equation right here. Okay, well, we're going to plug in x minus 1 here, we're going to plug in x minus 1 here, and so we get this. Does that make sense? That's just substituting x minus 1 in to this linear function. All right. And then when we evaluate at 1, we get a plus b from this one, this expression, and that zeroes out, and we get b plus 2 here. So then that gives us, cancel the b's, that gives us that a is equal to 2. So let's revise our knowledge of this second derivative. It's looking like 2x plus b. All right, integrate again. 2x integrates up to x squared, b becomes bx, and we pick up a constant of integration. But again, from our earlier relationship, we know that that's the first derivative evaluated at x minus 1 plus 2x, just from that process of taking those derivatives. So we'll plug in x minus 1, so we get x minus 1 squared plus b times x minus 1 plus c, and then 2x, because remember we are evaluating here at x, right? So this is x, but this is x minus 1 in here. All right. So we plug in x again. What do we get? Well, we get 1 plus b plus c on the one hand, and then these zero out, and we get c plus 2. The c's cancel, and that gives us b equals 1. So again, our updated knowledge of our first derivative now is x squared plus c. So we integrate that one more time, x cubed over 3 plus x squared over 2 plus cx plus d. Plug in 0, that's why I allowed 0. That tells us that d is equal to 0. Plug in 1, plug that in. 1 is equal to a third plus a half plus a sixth. That tells us c is equal to 1/6. And we get our proposed formula. And now the rest we can do simple. The base cases 0 and 1. I mean, we'll have to do only one of them, but you can see that those hold. And then the step here, you write that out. It's very straightforward algebra to prove that that induction works. So the formula that was suggested in this process actually does check out by induction. If you happen to know of any published sources that take this approach, let me know. I don't know that I've ever seen them. So anyway, thank you for your time. I hope you found it helpful.